All right, 1987 E&M number 1. This is a Gauss's law problem, and they didn't give you a picture this time, although they did outline a relatively straightforward situation in which we have a charge Q distributed uniformly throughout a spherical volume of radius big R. So I've drawn a picture down here. Black circle would be the radius of big R, that sphere of charge. And then we're going to have lowercase r being our variable. And they tell us straight out, use Gauss's law. And then for parts A and B, we're going to get the electric field outside, that's the blue, and then inside, that's the green. All right, so for outside, we're going to use Gauss's law, Q enclosed over epsilon naught equals integral E dot dA. So the Q enclosed, if we're entirely outside and this blue arc gets extended to be a circle or a sphere, it's going to enclose all of that charge, and the surface area of that sphere is going to be 4 pi little r squared. And when we substitute both of those guys into our Gauss's law equation above, we're going to get 1 over 4 pi epsilon naught times q, and then divide by r squared. All right, for part B, now our Q enclosed is going to be a little bit different because we're going to have to deal with the volume that we have enclosed here. Let me switch to green because that will match up with there. So our Q enclosed is going to be a little bit different because now we've enclosed some of the volume and therefore some of the charge. And this is a lot like the 1989 problem, except this time this is a little bit easier because we don't have an extra point charge at the very center. This time we just have this charge spread throughout the volume. So our Q enclosed is now going to be the ratio, the volume ratio. So the constants all cancel out and we end up with little r cubed over big R cubed. Substitute these guys into our Gauss's law equation. We're still dealing with a sphere, so the area is still 4 pi r squared. And our electric field is then going to become Q over 4 pi epsilon naught r cubed, and then an r. Notice I've written it this way so that we have all of our constants and then our 1 over variable. And then all of our, 1 over variable squared. And then all of our constants and then variable. So if we were going to graph this, we would have constant over thing squared, which gets us exponential, an inverse square law curve. And for this guy, we have constants and then thing, so that would be linear. And then when you put these two guys together, where you have the linear part inside, and then at big R, you switch to inverse square law. We saw this in class before we got closed down. I doubt that you will have any graphing to make, but you might need to describe the relationship. And this guy's an inverse square, and this guy is either linear or directly proportional, depending on which kind of language you would prefer to use. All right, part C and D. So for part C, what is the potential at the surface of the sphere? Now, they tell us the electrostatic potential is assumed to be 0 at infinity. So you go really far away, and they tell us that the electric potential is 0 at R is really big. So this is a way of saying that dV from really far away to the surface, oh, come on, here we go, is going to be, and we did this also in the 1989 problem, really far away to the surface. Now, what this is saying is use your answer from part A because you're outside and find your answer. So this is going to be V at the surface minus V at really far away. And they told us as part of the conditions that that guy's 0. And then this is going to be really far away to the surface of Q over 4 pi epsilon naught dr over r squared. So we have all these constants that go along for the ride, and then we integrate 1 over r squared, which gets us a minus 1 over r that we will evaluate between really far away and the surface. So a minus and a minus cancel each other out, and we get v at the surface is going to be equal to q over 4 pi epsilon naught 1 over r. Now, determine the potential at the center of the sphere. Now that we've gotten to the surface, we have to go from the surface into the center. Again, the analogy is climbing a mountain. So we've climbed the mountain, the foothills anyway, and now we're going to head up to the peak. Which means that for the inside integral, we're going to have to use our answer from B. So for part D, we're going to do v at 0 minus v at r is equal to the integral from r to little r of e inside dr. And by little r here, I mean 0. That 0 and that 0 need to be the same. All right, so v of r, we already have an answer for that. That's our answer to C. So we're going to use our answer to C right here. So v of 0 is going to be equal to q over 4 pi epsilon naught 1 over r minus integral from r to 0 of this function, q over 4 pi epsilon naught big R cubed r dr. So when we integrate just this guy, we're going to get r squared over 2, and we're going to go from r to 0. And that's going to be, once we plug that guy into there, take care of this minus sign, because remember, it's going to be the upper limit minus the lower limit, but then we also have this minus sign, which means now there's going to be a plus. So we're going to have q over 4 pi epsilon naught 1 over r, and the minus from the lower limit and the minus from the integral is going to become a plus, q over 8 pi epsilon naught r. So we're going to have to multiply that guy by 2 and that guy by 2. So 2q plus q is going to be a 3q. So that'll be 3q over 8 pi epsilon naught r. Also, if you're curious, this r squared here, so big R squared, and then we're going to have an r cubed there. And they're going to cancel out and be left with just this r down here. That's where that came from. And this will get us the potential at the very center of the sphere.